GCSE physics boosters, black body radiation. That's what this video is about. Okay, now all objects emit electromagnetic radiation, and this is called black body radiation. That's what it is. I mean, you are emitting radiation now. Infrared, you'd be able to see it with an infrared camera. And that is basically what black body radiation is. It's the radiation that things emit. Now, if an object is hotter than its surroundings, then it will emit more radiation than it absorbs. Okay, so this hot loaf of bread we've just taken out the oven it's absorbing and emitting, but it's emitting a lot more than it's absorbing. This object here, an object which is colder than its surroundings, will absorb more radiation than it emits. So this very cold ice lolly is emitting and absorbing, but it is absorbing more than it is emitting in a certain amount of time. So its temperature will get bigger, it will increase, and it'll probably melt. Now, an object which is at the same temperature as its surroundings, like Gordon the gnome here, will emit and absorb the same amount, the same amount of radiation in a certain time. It will absorb and emit radiation at the same rate. Now, the amount of radiation and the wavelength of the radiation depends on its temperature, how hot the object is. So let's start top left. There's some human beings. Now they're at about 37 degrees centigrade and they're just emitting infrared. Okay, so it's invisible to us unless you've got a special camera. They're emitting infrared radiation. Let's get a bit hotter now. This red hot piece of iron is at 500 degrees centigrade. It emits lots of infrared and also some red light as well. Yeah, red is a smaller wavelength than infrared, a higher frequency than infrared. Let's get hotter. This bulb filament, 2500 degrees centigrade, and it emits loads of infrared and all the wavelengths are visible, Roy G. Biv, which is why it looks white. And then getting hotter still, the sun, the surface of the sun is about 6000 degrees centigrade. It emits lots of infrared, lots of visible, and now some ultraviolet as well. So the amount of radiation that they emit gets more and more, but also the type of radiation. You see that the maximum frequency is getting higher, or if you like, the smallest wavelength is getting smaller. This is actually the spectrum of the radiation emitted by the sun. And looking at this diagram, you can see there's visible, the peak is visible, but we're also getting ultraviolet, we're also getting infrared. This is the spectrum of light emitted by the sun. For astronomers, spectra like this are very important. You can tell a lot about a star by looking at its spectrum. For example, a hotter star like a blue giant, like this is, I believe, a picture of Rigel, which is a blue giant in Orion. And its spectrum is very different. It emits higher frequencies. The peak, the shape is the same, but it's kind of shifted to the left because this is a much hotter star. It's much hotter than our sun. Now, what is a perfect black body? Well, you know that black surfaces are good absorbers and they're good emitters of radiation. And black surfaces don't reflect radiation very well. Now, a perfect black body doesn't reflect or transmit any radiation. Okay, it absorbs all the radiation that lands on it. So a perfect black body doesn't reflect anything, okay, or transmit anything. It absorbs everything, and that's a perfect black body. Now, interestingly, a perfect black body doesn't have to be black. I mean, this very hot piece of iron and the sun, they're black bodies, almost perfect black bodies, and they're not reflecting light, they're actually emitting it. The light that we see them with is actually coming from inside them. It's not a reflection of anything else. Okay, so don't think a black body has to be black. Okay, a black body, just learn that sentence there. A perfect black body does not reflect or transmit any radiation. It absorbs all the radiation that lands on it. Now, consider this. This is a greenhouse. How does a greenhouse work? Well, you've got radiation from the sun. We talked about the spectrum of light from the sun. Lots and lots of visible light coming through the glass as much as possible, which is why the whole thing's made out of glass. And this radiation from the sun, it goes in the greenhouse and it gets absorbed by the air inside the greenhouse, by the floor, by anything else in the greenhouse. It is absorbed. And then it is emitted, but not as visible, but as infrared. But the infrared radiation can't escape from the greenhouse. It gets reflected back in. So basically what happens is the temperature of the greenhouse warms up. Okay, the infrared radiation is trapped inside the greenhouse by the glass, and so the greenhouse warms up. And that's called the greenhouse effect. It's how a greenhouse works. Now, the Earth's atmosphere works in a very similar way. You've got radiation from the sun is falling on the Earth's atmosphere. Some of it is reflected. I think it's something like 21% is reflected back into space, but most of it enters the atmosphere and it's absorbed and it warms up the air and the land and the sea. And then it's emitted again as infrared, but the infrared, not all of that escapes back into space. It can reflect back towards the land or be emitted back in the direction of the land. So this heat energy is trapped inside the Earth's atmosphere. Is that a good thing or a bad thing? Well, in recent years, this is a very wordy slide, but I'm going to talk my way through it. In recent years, there's been much concern about the greenhouse effect. Basically because since the Industrial Revolution, okay, for the last 100 to 200 years, humans have added significantly to the amount of carbon dioxide in the atmosphere. So we've been putting lots of carbon dioxide in the atmosphere when we burn fossil fuels, and also industrial farming. There's paddy fields which produce methane, and also lots and lots of cows producing methane. And carbon dioxide and methane are greenhouse gases. They very much affect the amount of radiation which the atmosphere absorbs. Now, without greenhouse gases, we'd actually have big problems. The average temperature of the Earth would be about minus 18 degrees centigrade, not 15 degrees centigrade. Okay, so the greenhouse effect, we actually need it. However, because of what humans have been doing since the Industrial Revolution, we've had an effect on the average temperature of the Earth. And this global warming has caused climate change and flooding, which is currently getting worse. Okay, in the future, climate change and flooding could have devastating effects on the lives of many people. As the polar ice caps melt, sea levels rise, we get lots more moisture in the atmosphere and lots more flooding. And if we do nothing, then the temperature of the Earth's atmosphere will continue to rise, and it's going to cause big problems. Here's a couple of graphs which kind of support the idea that global warming is a big problem. Study them for yourself. It's the kind of thing you might get in an exam and have to describe what patterns you can see. The first one, temperature rise since 1850, which is about when the Industrial Revolution started. The goal, apparently, this is 2021, is governments are saying they're going to limit the temperature rise to 2 degrees by doing this, that, and the other. We'll wait and see. The second graph is how sea levels have changed. Now, it may be in millimeters, but 200 millimeters is 20 centimeters, and that is an awful lot. That means an awful lot of coastline is now underwater, and if sea levels continue to rise because ice caps are melting, again, that's going to be a big thing in the future. It's going to cause a lot of problems. So what can we do? Our economies have been based on burning fossil fuels for a long, long time, and industrial farming as well, big scale farming. So what changes need to be made? And I'm just going to leave it there.